Good morning, students. Today we will discuss the fundamental properties of eigenvalues and eigenfunctions for symmetric kernels. First property we discussed yesterday, and the second property is the eigenfunctions of a symmetric kernel corresponding to different eigenvalues are orthogonal. So in order to prove this, let us take two different eigenvalues, lambda 1 and lambda 2, and the corresponding eigenfunctions we have taken phi 1s and phi 2s. Now because lambda 1 is the eigenvalue and phi 1s is the corresponding eigenfunction, therefore the symmetric integral equation will be satisfied. So we get phi 1s is equal to lambda 1 into integral kst phi 1t dt. In the same way, lambda 2 is the eigenvalue and phi 2s is the corresponding eigenfunction. So therefore, the corresponding symmetric integral equation will be satisfied and gives the value phi 2s is equal to lambda 2 integral kst phi 2 t dt. Now, let us write the equations 1 and 2 in the notation form. This can be written as phi 1, and because in the operator form this is k phi 1, so this equation will become phi 1 minus lambda 1 k phi 1 is equal to 0. And in the same way, the equation second in the form of operator notation, that can be written as phi 2 minus lambda 2, this is k phi 2 is equal to 0. So we have obtained these two equations. Now let us take conjugate of the equation 4, and using the first property, let us take the conjugate. If we take conjugate in the equation 4, we get phi 2 conjugate minus lambda 2 conjugate into k star phi 2 conjugate is equal to 0. Now because lambda 2, that is eigenvalue of a symmetric kernel, and yesterday we discussed that the eigenvalues for a symmetric kernel are always real. So lambda 2 conjugate will be same as lambda 2. So we get the equation phi 2 conjugate minus lambda 2 into k star into phi 2 conjugate is equal to 0. Now let us write this k star phi 2 star in the by using the definition of the operator k star. So this will become phi 2 star minus lambda 2 into integral k star st phi 2 star t dt. Thus now multiplying the equation 3 by lambda 2 into phi 2 star, we get the equation lambda 2 into phi 2 star into phi 1s minus lambda 1 lambda 2 into integral kst phi 1t phi 2 star s dt is equal to 0. Now let us multiply this equation 6 by lambda 1 phi 1s. So if we multiply by lambda 1 phi 1s, this term will become lambda 1 phi 1s into phi 2 star s. Here by multiplying with lambda 1 phi 1, this term will become lambda 2 into lambda 1 into integral k star st phi 2 star t phi 1s dt is equal to 0. Now let us integrate the equation 7 and equation 8 with respect to s, and subtracting the resulting equations, we get lambda 2 minus lambda 1 into integral of phi 1 into phi 2 conjugate is equal to 0. Now because lambda 1 and lambda 2 are the distinct eigenvalues of the symmetric kernel, therefore lambda 2 minus lambda 1, that is not equal to 0, because this product is 0 and this term is non-zero, therefore this quantity will be 0. So we get integral phi 1 into phi 2 conjugate is equal to 0. Now by definition, this is inner product of function phi 1 with function phi 2. So we get inner product of function phi 1 with function phi 2 is 0. And we know that if the inner product of two functions, that is 0, the functions are orthogonal functions. So this proves the property that for a symmetric kernel, the eigenfunctions corresponding to different eigenvalues are orthogonal. Now let us discuss the third property. Now the property 3 is that the sequence of eigenfunctions of a symmetric kernel can be made orthonormal. Now we are given a sequence of eigenfunctions corresponding to a certain eigenvalue. So let us take corresponding to a certain eigenvalue, there are m linearly independent eigenfunctions, say phi1, phi2, phi3 and so on up to phi m. Now we can use Gram-Schmidt procedure. According to this procedure, if we are given a sequence of linearly independent functions, we can convert this sequence into an orthonormal sequence. So by using this process, the sequence of linearly independent functions can be converted into an orthonormal sequence. On the other hand, for the distinct eigenvalues, the corresponding eigenfunctions are orthogonal by the second property, and also every function can be normalized by dividing each function by its norm. So in this way we get a sequence of eigenfunctions for the symmetric kernel which is orthonormal sequence. So this proves the third property. Now the next property is the multiplicity of non-zero eigenvalues is finite for a symmetric kernel, for which the double integral of square of mod of kernel kst, that is finite. Such kind of kernel which satisfies this condition, that is called square integrable kernel. So now let us take corresponding to a non-zero eigenvalue lambda, we have the linearly independent eigenfunctions which are given by phi1 lambda, phi2 lambda, phi3 lambda and so on, phi n lambda. These are the linearly independent eigenfunctions corresponding to the non-zero eigenvalue lambda. Now as we already discussed, by using Gram-Schmidt procedure we can find the linear combinations that forms an orthonormal system. So let us take the corresponding orthonormal system of the functions, that is uk lambda conjugates. Now let us write the kernel kst in the form of the series having the scalars alpha i's, and it is given by summation alpha I ui lambda conjugate. Here these alpha I are the scalars which are known as Fourier coefficients, and by definition of Fourier coefficients are given by the inner product of this function, this kernel k with the functions ui lambda. So the inner product of the kernel k with the functions ui lambda, that is given by integral kst into the conjugate of these functions, which is ui lambda. Now multiplying and dividing by lambda and taking lambda inside the, and we get lambda inverse into lambda integral kst ui lambda t dt. Now because ui lambda, they are the eigenfunctions corresponding to the eigenvalue lambda, so they will satisfy the symmetric integral equation. Now the symmetric integral equation is gs is equal to lambda integral kst gt dt. So here replacing gs by ui lambdas, inside the integral also gt is replaced by ui lambda t. So by using this, here we get the values of alpha I which are given by lambda inverse into ui lambda s. Now let us use Bessel's inequality. So by Bessel's inequality we have summation alpha I mod square is less than or equal to kst norm square. Now by using the definition of norm means square root of inner product of the function with itself. Here the function is kst, so kst norm square means inner product of the function kst with itself. Now from the equation 1, substituting the value of Fourier coefficients alpha i's here. If we put the value of alpha I here, the inequality becomes summation over all I lambda inverse ui lambda mod square is less than or equal to. Here we have used the definition of inner product. By definition of inner product, this is integral of product of first function with a conjugate of second function. Now from here we get summation lambda inverse square into ui lambda mod square is less than or equal to integral kst mod square dt. Now by using the integration of both sides with respect to s, we get summation lambda inverse square. Here integration of this with respect to s. On the right hand side also we have integrated with respect to s. Now the kernel is square integrable, this expression is finite, so this is less than infinity, and also the sequence of the functions ui lambda, that is orthonormal sequence. Therefore the norm of each function in the sequence, that will be 1. So therefore ui lambda norm, that is 1. Substituting the values here, this will become summation over all I lambda inverse square. This is 1, this is finite, so we get summation over all I lambda inverse whole square, that is finite. Thus we can say that the multiplicity of every eigenvalue lambda, that is finite. So this proves the fourth property of eigenvalues and eigenfunctions for the symmetric kernels.